This is a continuation of Module 9. We just went through Part C of Module 9, and now we'll start Part D on rehabilitation design strategies of flexible pavements. The sections of Module 9 that follow will explain and discuss the different options or strategies for rehabilitating flexible pavements, and each will be discussed separately. As noted in a previous part or earlier within Module 9, the rehabilitation strategies and design of flexible pavements are grouped into three different areas. The first, surface modification of asphalt pavement with non-structural overlays. Second, asphalt structural overlays with or without modifications to the existing surface. And finally, concrete overlays themselves. So we will go through each one separately. Starting with surface modifications of asphalt pavements without structural overlays. As mentioned earlier, surface modifications of asphalt pavements without structural overlays or improvements are not directly included in the Pavement ME design software. So this session or section provides some suggestions on how this option can be considered and used in the Pavement ME design software. Basically, there's three different areas of surface modification, or surface modification is grouped into three areas that do not include structural rehabilitation. The first is milling with some type of non-structural surfacing. The second is other types of non-structural maintenance activities. And then hot in place recycling with or without non-structural surfacing. The hot in place recycling layer can be simulated as a ultra-thin overlay or other surface treatments or modifications that are less than 1 inch in thickness. The key is that the thickness is less than 1 inch, which is the assumption for non-structural overlays or non-structural rehabilitation techniques. So flexible pavement is assumed to be structurally adequate with surface modifications, and rehabilitation without structural overlays is adequate or should be sufficient. So for this rehabilitation strategy, we use the new flexible pavement design strategy that includes a maintenance activity or the strategy folder within the Pavement ME design software. These are non-structural activities. As an example, if we have in 2008, say August 2008, construction of a pavement that has 16 years of surface, which would be 2024, and then we're going to add an additional 15-year rehabilitation design, and those total 31 years of the design life, starting from the base construction date and or original pavement construction date, as well as the traffic opening date from 2008 plus 31 years, which would be 2039 for the final. But placing the surface modification in 2024 would equal 16 years of service life since the original pavement construction date. And this is just an example. So the inputs to using the maintenance strategy in the Pavement ME software is date of the placement of that strategy, say September 2024, the type of activity, say micromill and with microsurface, and the initial IRI after the activity has been placed, and as an example, 55 inches per mile. So the 2008 construction year was 16 years of service plus a 15-year rehabilitation design in year 2024 means that's when we're placing the maintenance strategy for the surface modification. So this is somewhat similar to restoration of concrete slabs, where we're dating back to the original construction of the flexible pavement because the pavement is structurally adequate. And then we're going to look at placing surface modification, non-structural rehabilitation activities, with the exception of maybe some localized pre-overlay repairs if needed. And then we're going to see if the original pavement construction with our non-structural maintenance activity then satisfies an additional 16 years of, or an additional 15 years of service life. For basically an overlay, for basically a design life of the original pavement of 31 years. So remember, these activities of surface modifications are non-structural and are less than 1 inch in thickness. The type of maintenance or surface modification has really no impact on the distress prediction other than the initial IRI after placement. The distress predictions or calculations are the same as for new flexible pavement. So execute the program or run the program just like for a new flexible pavement design going back from the original construction date through the initial period of performance where the pavement is still structurally adequate, and then checking the additional 15-year service life or 20-year service life using these non-structural maintenance activities and or surface modifications. So that is one way and a suggested way for flexible pavements that are found to be structurally adequate, have very little distress other than maybe surface distresses confined to the surface, and we're going to use a non-structural overlay or non-structural surface treatment and or maintenance strategy to determine whether the pavement, the existing or original flexible pavement, will perform throughout the extended service life and meet all the performance criteria, which would be the same for a standard new flexible pavement design, as we discussed or considered in Module 6 for flexible pavement design. Now let's move on to asphalt structural overlays. This will be the next session within Part D. So these are different asphalt structural overlays that are included in the Pavement ME design software. The first asphalt overlay or rehabilitation, well, the first is where the first asphalt overlay and or rehabilitation is placed. In other words, the original flexible pavement does not have any other rehabilitation activity. The other category is for multiple asphalt overlays or rehabilitation. In other words, the flexible pavement already has one or more asphalt overlays or rehabilitations, and we're designing a future overlay or rehabilitation activity that already has that has already been rehabilitated in previous years. These two are very similar and only include slight differences, which we will identify in the following slides. The basic difference between the single or first and multiple asphalt overlays is an asphalt overlay has already been placed for the multiple asphalt overlays. So in the pavement structure simulated that we saw when we looked at had the software open, it has a future asphalt overlay, an existing asphalt overlay, and then the original pavement structure, compared to the first asphalt overlay that has our future asphalt overlay and then only the existing or original flexible pavement or asphalt pavement structure. All other layers, including the new asphalt layer, are simulated in the same way. So the first asphalt overlay or rehabilitation. 3 dates are used for the first asphalt overlay rehabilitation option. In other words, first overlay rehabilitation design type. The pavement type in the Pavement ME software is AC over AC. And so one of the dates is the existing pavement construction date. Second is the proposed overlay construction date. And then the traffic opening date, which is the basic 3 dates that are needed for just about all rehabilitation activities. An additional date is required for the multiple asphalt overlays and rehabilitation. Again, multiple overlays, rehabilitation, AC over AC over AC is the term used in the Pavement ME design software. So the additional date that's required for the multiple asphalt overlays is the existing overlay construction date. So there's 4 dates for the multiple overlays, and obviously one of those is the existing overlay construction date. So the asphalt structural overlay, the performance criteria basically is the same for new flexible pavement design. The only difference is the additional criteria that is specific to asphalt overlays, which include reflection and new bottom-up fatigue cracks and or reflection and new thermal transverse cracks are the new design criteria. The program still calculates AC bottom-up fatigue cracking. This is new in the asphalt overlay, and also calculates new asphalt thermal or transverse cracks specific to the asphalt overlay. As mentioned previously, the reliability value for these is 50%, and the user cannot change that. And again, the reason it's 50% is because reliability is only applied to what we can see and measure at the surface, which is the combined reflective and new bottom-up fatigue cracks, reflective and new thermal or transverse cracks. So reliability for these 2 criteria cannot be changed because they only represent new cracks, new fatigue cracks, new thermal cracks in the asphalt overlay. And the reliability is applied to, as we just previously noted, to what we can see and measure at the surface. The reflective plus new cracks in the asphalt overlay. The total combined fatigue and total combined thermal or transverse cracks. Now let's move to the AC layer properties screen or the design properties folder and the AC layer properties screen. All asphalt layer properties are the same as for new flexible pavements. The endurance limit and the multiple layer rutting calibration coefficients we discussed specifically in Module 4-4, and these are identical to the asphalt structural overlay under this module. And the layer interface friction between each of the layers is the same as also for new flexible pavement design. 1 means full friction, 0 means no friction or full slip conditions. The MEPDG Manual of Practice recommends that full interface friction be used unless there is a reason, like for flexible pavement rehabilitation, like debonding in the existing or between the existing asphalt layers themselves, and other material defects between the layers. Under design properties, now the rehabilitation screen. And this is rehabilitation input level 2. We have a mill thickness, which we will define and how that's used in a latter section of this module. The other thing is we have the amount of surface distress, bottom-up fatigue cracks that are entered, its severity, and then the default load transfer efficiency, which was defined from global calibration. The next critical input is thermal cracking in feet per mile, the amount and the severity and the load transfer efficiency. As discussed earlier in this module, load transfer efficiency can be actually measured on the project. And if that is measured, the user can enter the specific value as a user-defined value under the severity level. The item is the rut depth, the total rut depth that has been broken down by individual layers of the asphalt and or unbound layers. For multiple asphalt overlays, the alligator fatigue cracks observed at the surface are assumed to be bottom-up cracks from the existing asphalt pavement. So if we have multiple overlays, if there's fatigue cracks that are measured at the surface, the bottom-up fatigue cracks, those cracks are assumed to propagate or to be through the existing asphalt overlay as well as the asphalt layers of the original flexible pavement construction. And that is true as well as for transverse cracking. So this is a summary of rehab input level 2 for flexible pavements. Rehab input level 1 for asphalt structural overlays of flexible pavements. So this is rehab input level 1, again, the mill thickness. The difference is the bottom-up fatigue cracks. That value is no longer, the bottom-up fatigue cracks from the visual distress survey is no longer entered by the user. Bottom-up fatigue cracking damage is determined through the back-calculated elastic layer modulus of the existing asphalt layer. In other words, the damaged master curve versus the undamaged master curve that we previously discussed in an earlier part of Module 9. The transverse cracking is the same, but the only difference is the fatigue cracking is not entered by the user. It's defined through the back calculation of layer moduli. Rehab input level 1, this shows now the structure and now the mechanical properties for the existing asphalt layer. This would be the existing asphalt layer in the original construction, and this is located under Structure, the Structure folder, and the Mechanical Properties. So the rehab input level 1 is the asphalt elastic layer modulus, either a single value or multiple values are entered in the Pavement ME design software. So we can have 1, 2, or 3 back-calculated modulus values that are a function of the mean pavement temperature at the time of deflection testing. In general, most of the time this is going to be one entry because the deflections are generally not measured over a wide enough temperature change for looking at the effects of temperature on the back-calculated layer moduli. Generally, there has to be at least a minimum of 10 degrees Fahrenheit difference, preferably around 15 degrees Fahrenheit difference, to see any difference in the back-calculated elastic layer moduli based on temperature, and not some other on-site variable like debonding in areas, stripping in areas along the project. But this is where the back-calculated layer moduli data for the existing asphalt layer are basically entered. If we have multiple asphalt overlays, not just a single original pavement, but we have an existing asphalt overlay and an original pavement construction, how is this entered or simulated? Back-calculated different moduli or combinations are combined into one layer, but treated as two in the Pavement ME software. So typically, we're only going to back calculate for one asphalt layer regarding the original construction versus an existing overlay. And that value will be entered for both the existing overlay in terms of this table, in addition to the table for the original construction of the asphalt layer. So they would be the same. If they're different, say we have a different back-calculated layer modulus value for either different original construction or base materials, then those will be entered separately for whatever is simulated in the pavement structure. And we'll give an example of that shortly. So this just shows a screenshot of where we have the multiple back-calculated layer modulus that are at different temperature, mid-depth temperatures of the asphalt layer. This could be where this deflection testing started in the morning, early in the morning when the pavement was cooler. And then this could be from the testing done late in the afternoon, especially if it's clear with the sunshine. The temperature at the mid-depth of the existing asphalt layer will be higher, and so the back-calculated layer moduli should be lower. So this is simply a screenshot of the back-calculated asphalt layer modulus values when the existing asphalt pavement is simulated as one single layer, but the deflection testing was grouped into two different temperatures. Not necessarily design segments, but within the same design segment, just different temperatures. This is a screenshot of the back-calculated asphalt layer modulus values when the existing asphalt pavement is simulated as two asphalt layers, and the deflection testing was conducted at one pavement temperature. So we have the back-calculated layer modulus entered for the lower asphalt layer of the original construction, and those values are entered for that layer, existing asphalt base or lower layer. We then have the upper asphalt layer the existing asphalt wearing surface or upper layer, and the back calculated layer modulus values entered for that layer. So we can enter different back calculated layer modulus values for different layers within the asphalt pavement. They could include, for the multiple asphalt overlays, the original pavement structure and then the asphalt overlay, assuming it's thick enough for the asphalt overlay, the existing asphalt overlay that was placed after the original pavement construction, especially if there's some reason why the two would exhibit significantly different load response differences or different stiffnesses. Now, milling. We said we would come back to the definition of milling, and this basically slide defines the milling depth and what value in terms of layer thicknesses of the asphalt layer should be entered in the Pavement ME software for rehabilitation design. So what asphalt thickness is entered in Pavement ME when milling the existing asphalt layer. So if we have a mill thickness of, let's say, 2 inches for this pavement structure or core from the pavement structure, the total core thickness is 9 inches. The wearing surface is about 1.75 inches, as you can see, which has become debonded. So the rehabilitation strategy is to mill this wearing surface that is debonded and then place an additional structural asphalt layer. So we're going to mill off 2 inches to ensure we're below the debonded layer. And then, so we have basically 7 inches of the existing asphalt that remains, and the wearing surface will be removed. So what values do we enter in Pavement ME for the existing layer? The remaining asphalt thickness of 7 inches is entered into the Pavement ME software for the existing asphalt layer. So the thickness of the existing asphalt layer is not the thickness that's entered. It's always the asphalt thickness that remains and is representative of the condition at overlay. So since we milled off 2 inches, which leaves 7 inches, 7 inches is entered into the thickness of the existing asphalt layer for our rehabilitation design in the Pavement ME software. The other item to be entered, which we have mentioned previously, is load transfer efficiency. This is under the rehabilitation tab of the design features or design properties. So the load transfer efficiency. So the load transfer efficiency can be measured for transverse cracks, but not for fatigue cracks. For fatigue cracks, it is estimated through the global calibration process or through a local calibration process. The global load transfer efficiency values for both transverse and fatigue or alligator crack were estimated through global calibration and are related to crack severity, which we showed when we had the software open. Remember, the fatigue or alligator cracks entered are only for the bottom-up fatigue alligator cracks and not for top-down cracks, top-down fatigue cracks. LTE, or load transfer efficiency, is a very important input and has a significant impact on fatigue and transverse cracks that are predicted because it relates to the differential vertical deflection across the crack or joint in the flexible pavement. The differential vertical deflection defines the shear component of the stress intensity factors for reflection cracking predictions that we previously discussed earlier within Module 9. So, as shown, the top graph is total fatigue cracking predicted in terms of percent lane area. The red curve, or the cross marks, show high severity fatigue cracks, which include an LTE of 0.1. So that cracking begins very rapidly and expands very rapidly. So the total number of fatigue cracks existing in the existing surface will reflect through the asphalt overlay in a very short period of time. The blue shows the medium crack severity, which is point and low transfer efficiency of about 0.4. These also propagate reasonably fast and reach the maximum amount of fatigue cracking in the existing asphalt layer fairly shortly. The green represents the low severity crack, or low transfer efficiency of about 0.8. And so once we start getting into higher low transfer efficiencies, which means a much lower differential vertical deflection, it takes some time for those cracks the cracks in the existing pavement, fatigue cracks in the existing pavements, to propagate through the asphalt overlay. The bottom graph is for the total transverse cracks in terms of feet per mile. Same types of information, total transverse crack as a function of age. So the red is low severity crack, the blue is medium severity crack, and the green is low severity crack, transverse cracks in the existing asphalt layer. So once the cracking starts, even with low severity, it's going to propagate very rapidly because the transverse cracks are initiated at the bottom of the overlay, and then the shear stress intensity factor, even though the differential vertical deflections are relatively small, they're going to propagate fairly rapidly. So low transfer efficiency is very important in terms of the amount of cracks in our existing asphalt layer, whether they're bottom up fatigue cracks or transverse cracks. They're going to reflect. That is a very important variable in determining the magnitude of the total cracking in the asphalt overlay. So very briefly now, let's discuss the different options where some types of interlayers are placed between the existing asphalt layer and asphalt overlay to mitigate reflection cracks. Again, reflection cracks are composed of our three different options: shear, which is the more important, tension, and bending. And so what type of materials can we place between our asphalt surface and or overlay and the existing, say, concrete pavement or existing asphalt layer or existing of the existing flexible pavement? So we can use stress or strain absorbing membrane interlayer, such as seal coats and other engineered interlayer, to try to mitigate the propagation of reflection cracks into the asphalt overlay. We can look at reinforcement of asphalt overlay or geogrids, which are not considered in the Pavement ME design software. So we are considering interlayer, seal coat, some other type of interlayer. Geogrids are not considered. Other strategies also include modification of the asphalt overlay mixture, different types of polymers, other types of binder modifications that can be included in the lower part of the overlay, as well as crack control method. The crack control method is not also considered in the Pavement ME design software, but we're going to go through a slide shortly because that method, that mitigation method of crack control, in other words, sawing and sealing above the transverse cracks or transverse joints in a concrete pavement, has been considered successful. So the stress or strain absorbing membrane interlayer seal coats and other engineered interlayers. The interlayer is typically or is less than an inch as assumed in the Pavement ME design software. So it is a non-structural layer. And so that layer, that non-structural layer, would be included as part of the overlay thickness. So if we're placing, let's say, a half-inch seal coat, if we're placing a 3/4 inch inner layer, some of the ground tire rubber membrane inner layers that have good, relatively good success in mitigating reflection cracking, the thickness of that inner layer would be included in the thickness of the overall asphalt overlay that we're entering into the Pavement ME design software. And simply this just shows of an inner layer that's been placed. Specifically, this is above transverse joint and concrete pavements. And some of these engineered interlayers can be relatively effective in mitigating the reflection cracks through asphalt overlays. Unfortunately, the calibration that was done in Pavement ME, the global calibration on using asphalt overlays of rigid pavements like jointed plain concrete pavements and or asphalt overlays of flexible pavements with existing fatigue cracks as well as transverse thermal cracks, those sections that were used in the calibration did not exhibit any benefit. So our overlay options, our rehabilitation options in the Pavement ME design software that includes seal coats and interlayers, basically there is no difference, and so there is no benefit to using those layers because the global calibration did not exhibit a difference. As a result, it is strongly encouraged that local agencies that have experience with these interlayers include those in their local calibration process because some of the selected engineered interlayers can be effective and provide a definite benefit for mitigating reflection cracks through an asphalt overlay. The other overlay strategy is modification of the asphalt mixtures treated as a new asphalt layer greater than an inch with appropriate layer thicknesses. So that would be included as part of the asphalt overlay of the existing flexible pavement. There is a crack control method. It's not considered in Pavement ME, but has been considered successful. This method is not really applicable to asphalt overlays of flexible pavements, but it's being mentioned in terms of asphalt overlays of concrete pavements or jointed concrete pavements. These have been, or this method or strategy has been found to be effective in mitigating or in the performance of the asphalt overlay because reflection cracks will not occur if the asphalt overlay is sawed and sealed in the correct location above the joints in the concrete pavement. So as mentioned earlier within this module, asphalt structural overlay with surface modifications are an option. Hot in place recycling of the asphalt wearing surface, cold in place recycling of the asphalt layers, as well as full depth reclamation of the flexible pavement. All of these three surface modifications methods are not specifically included or simulated in the Pavement ME design software. The information included within this session of Module 9 provides suggestions on how these rehabilitation options or strategies can be considered as a rehabilitation option in the current version of the Pavement ME design software. So let's start with hot in place recycling. This is an asphalt surface overlay, structural overlay with surface modification, and that surface modification is the hot in place recycling layer. And that is simulated as a new asphalt layer. As we noted earlier, if the hot in place recycling layer is an inch or less, then that should be combined with the asphalt overlay or structural overlay thickness. If it's thicker, then it can be simulated as a separate layer in the asphalt overlay. However, the assumption for the hot in place recycled layer is that it is designed as a dense graded asphalt layer. So all of the asphalt mixture properties are the same as for a new dense graded asphalt layer. And again, if the hot in place recycled layer is less than an inch below the structural overlay, that thickness or the thickness of the hot in place recycled layer should be added to the asphalt structural overlay thickness. Now for cold in place recycling strategy. Cold in place recycling layer is typically or can be simulated as a new asphalt layer. So when the cold in place recycling layer is designed as a dense graded asphalt layer, the properties are the same as for a new dense graded asphalt layer. Cold in place recycled layers are generally greater than an inch, so they generally can be considered as a separate asphalt layer. Cold in place recycling typically can be used when the distresses are confined to the wearing surface and or start propagating below the wearing surface. And in addition, there could be some material surface defect, like longitudinal aggregate segregation or truck-to-truck segregation from the construction placement process, or raveling at the surface, or other types of surface-related distress. So cold in place recycling can be considered as a dense graded asphalt layer as long as it is designed as a dense graded asphalt layer. Keep in mind, only 4 asphalt layers can be included in the Pavement ME design software, which typically includes 1 or 2 original asphalt layers, a cold in place recycling layer, and a new asphalt layer. That would total then 4. So there is a maximum of 4 asphalt layers that can be used in Pavement ME, or the Pavement ME software is restricted to the use of 4 asphalt layers. In summary, cold in place recycling can be included as a rehabilitation strategy. If it is not designed as a dense graded layer, then that condition will be discussed later in at the end of this module. Full depth reclamation. For full depth reclamation, that's where we're recycling the existing asphalt layer with portions of the aggregate base or underlying the structure. It is designed as a new flexible pavement because we are totally destroying the existing asphalt layer, similar to rubbleizing jointed plain concrete pavement or continuously reinforced concrete pavement. So for the FDR layer, or the full depth reclamation, if it is designed as a dense graded stabilized layer, then it is treated as a new pavement, designed as a new pavement. If the stabilizer is Portland cement, so we have a chemically stabilized layer, that was covered under Module 6-2 on semi-rigid pavements. So again, it is designed as a bound layer, a bound dense graded stabilized layer. So if we're using some kind of cementitious type material, then Module 6-2 would apply because this would be a semi-rigid pavement. If asphalt or the stabilized layer using some type of foaming, emulsion foam, asphalt foam, or emulsion treated, and it is designed as a dense graded stabilized layer, then that would be treated as a new flexible pavement, and that asphalt stabilized layer would be treated as any other asphalt layer in new flexible pavement design. However, if only a small amount of additive is added to the treated or FDR, full depth reclamation layer, and that goes for either a cementitious material or an asphalt or bituminous material for full depth reclamation, or even if only a small amount of additives is used for the cold in place recycled, then then the FDR full depth reclamation is treated as an unbound granular layer. And that treatment or simulation is included on the next couple of slides, or explained on the next couple of slides. So in summary, as long as the full depth reclamation, as well as the cold in place recycled layer, is designed as a dense graded layer or bound dense graded layer, then that would be treated as a new semi-rigid pavement or new flexible pavement. So what if only a lower amount of additive, either a cementitious type material or some type of emulsion or no emulsion, is used in the full depth reclamation? It's just the asphalt is combined with the aggregate base or a portion of the aggregate base. Then how do we simulate that? So as a reminder, chemically stabilized base layer, that's C Module 6-2 for semi-rigid pavement. We're adding asphalt or bituminous, and it's a stabilized bound base layer, C Module 6-1 for flexible pavement. If it's not designed as a stabilized bound layer, then simulate as an unbound base layer itself. So these next couple of slides will go into a little bit more detail when that FDR layer is not designed as a bound layer. So we're going to simulate it as an unbound layer. This shows the full depth reclamation layer that's not designed as a bound layer for the modulus. The unbound layer, the properties of the unbound tab and the sieve, the gradation, would be considered the same for the type of material. The modulus is generally the suggestion is simulate the unbound layer with a higher resilient modulus, but that depends on the amount of additive and type of additive that's mixed in with the full depth reclamation layer. The other item is, do we consider it an annual representative value, or do we allow the program to modify the resilient modulus as a function of degree of saturation? The suggestion is allow the program to change the resilient modulus based on changes in water content throughout the design period. But again, that depends on the amount of additive as well as the type of additive that's mixed into the full depth reclamation layer. In addition, how much asphalt is being mixed in with some of the aggregate base materials that are present in the existing flexible pavement structure. So this is a user-dependent. There's information included in the MEPDG Manual of Practice for providing additional information in terms of the suggestions. Also, Module 6-2 on semi-rigid pavements also provided some recommendations from adding cementitious type materials as part of the full depth reclamation. And then the same type of thing would apply to adding bituminous type materials, foamed emulsions, asphalt emulsions, to the full depth reclamation layer. So now we're going to we'll move to the next section on Portland cement concrete or overlays of the flexible pavements. And there are three types. The three types are jointed plain concrete overlays of flexible pavements, continuously reinforced concrete pavement overlays of flexible pavements, and then short jointed plain concrete pavement overlays of flexible pavements. We're going to start with items that are similar in the Pavement ME design software in terms of JPCP as well as CRCP overlays of flexible pavements. So the existing flexible pavement is typically badly deteriorated. Milling the existing surface could be required, at least to get a level platform for placing the JPCP or CRCP overlay on the flexible pavement. Structural improvement is generally needed. Reflection cracking is not considered, but it's typically not an issue. And then the other site factors that need to be considered are potentially facilities with heavy or slow-moving trucks, like at intersections. Clearances required must be met if we have curb and gutter and or guardrail. In terms of adjacent features, that needs to be considered. And then more importantly, lane closure time for keeping the lane closed for placing a JPCP or CRCP overlay above the flexible pavement. So these are all considerations that need to be included for designing concrete overlays of flexible pavements. The design process for the JPCP overlay design is the same as for new jointed plain concrete pavements with an asphalt base. And this was discussed and described in Module 5-1. The inputs and design features for the jointed plain concrete pavement overlay are the same as for a new JPCP. The difference is we have fatigue cracking that's entered for the existing asphalt layer. For basically rehabilitation input level 2 or rehabilitation input level 1, where deflection testing is used to identify the in-place damage or in-place condition of the existing asphalt layers. Inputs for the existing asphalt layers were discussed earlier within this module, related to rehab input level 1 versus rehab input level 2. The CRCP overlay design process is the same as for new CRCP with an asphalt base, and this was presented and discussed in Module 5-2. The inputs and design features for the CRC overlay are the same as for a new CRC pavement. The fatigue cracking in the existing layer from the visual distress surveys needs to be entered for the existing asphalt layer, or the back calculated layer moduli of the existing asphalt layer are entered to define the condition and damage of the existing asphalt layer. In other words, rehab input level 1 versus rehab input level 2 for flexible pavement design. The inputs for the existing layers were discussed earlier also within this module. And those discussions both apply to JPCP and or CRCP overlays of flexible pavements. This just shows a schematic or illustration of the layer structure where we have the JPCP over our existing flexible pavement, and then the other is where we have a CRCP overlay over the existing flexible pavement. So basically all the layer properties are the same as previously discussed. The difference is in the characterization of the existing asphalt layer. Rehab input level 1, that's using deflection test to define the amount of damage in the existing asphalt layer. In other words, the amount of damage in the existing asphalt layer, regardless of whether it is a JPCP or CRCP overlay. So the fatigue cracking basically is defined through the back calculated layer moduli, the damaged modulus versus the undamaged modulus, as we previously discussed. It's entered in exactly the same way that when we had the software open, and as we discussed for structural asphalt overlays of asphalt pavements. So that represents the same in terms of the severity and the low transfer efficiency. Again, for concrete overlays of flexible pavements are not used because reflection cracking is believed not to be an issue on concrete overlays of flexible pavements. The reason the in-place damage is used is that it reduces the stiffness or modulus of the existing asphalt layer. So if you have a flexible pavement that has a lot of damage, a lot of cracking, then the layer modulus of the asphalt layer is going to be reduced, and so that will affect the critical pavement responses for designing a JPC or CRC overlay. And this simply shows the rehab input level 1 for JPCP or CRCP overlay of flexible pavements. The non-destructive back calculated layer modulus, the frequency, and the temperature, that value is entered in terms of the mechanical properties for the existing asphalt layer. The other rehab input level 1 option is for the modulus of subgrade reaction. Again, this was discussed within Module 6-1 as well as in Module 6-2 in terms of determining whether the modulus of subgrade reaction is either measured or is allowed to be calculated by the Pavement ME software or program. So it's exactly the same as for new rigid pavement design, and the same as for rigid pavement rehabilitation, as discussed in Module 8. This is Rehab Input Level 2. And again, it's now the fatigue cracking, the total amount of bottom-up fatigue cracking is entered into the software because that now defines the damage index, which defines the in-place layer modulus of the existing asphalt layer. Again, the severity level and the low transfer efficiency are not applied because that has to do with predicting reflection cracks. And as you remember earlier within this module, reflection cracks are not considered to be an issue in concrete overlays above flexible pavement, so they're not considered. This now just shows the performance criteria of the jointed plain concrete overlay of a flexible pavement. They are identical to what's used and considered for new jointed plain concrete pavement design. So there's no difference between the two. This also shows now the CRC overlay, the performance criteria of a CRC overlay of a flexible pavement. Again, it's identical to the performance criteria used for new CRCP designs, which were discussed in Module 6-2. Kind of the last item now for concrete overlays of flexible pavements is going to be on short jointed plain concrete pavements above the flexible pavement. The definition is a short jointed plain concrete overlay is bonded to an existing asphalt pavement. These are relatively thin slabs, 4 inches to 8 inches, and they have short joint spacing, generally 5 by 5 to an 8 by 8 foot slab, depending on the dimensions or the lane width of our flexible pavement, as well as other site-specific features. This just shows a photo of a short jointed plain concrete pavement using 6 by 6 foot joints that were placed over an asphalt, which was placed over an existing jointed plain concrete pavement. The performance criteria for short jointed plain concrete pavements are shown on this slide. Currently, the current version of Pavement ME software, version 3, only includes the longitudinal cracking in terms of percent cracked slabs for short jointed plain concrete pavements. Terminal IRI is not considered. Transverse cracking or other types of cracking on short jointed plain concrete pavement overlays are not considered. Only the longitudinal cracks in these slabs are considered. And the longitudinal cracks are kind of shown in both of these photographs under the wheel loads within the wheel path. The longitudinal cracks of these short slabs are shown in the photo. So that is the only performance criteria that is used. So the joint design of the short jointed plain concrete overlays of asphalt, typical spacing is either, again, 6 by 6, 5 by 5, depends on the lane width to ensure the longitudinal joint is basically between the wheel paths of the trucks. The range listed by the software as either 5x5 or 8x8, depending on the lane width. Generally, no dowel bores are in the transverse joints. Thus, most of these short jointed plain concrete pavements have been used on low to moderate truck traffic, used at intersections that have relatively low truck traffic. Tie bars can be included in the longitudinal joints to make sure the longitudinal joint between the short jointed plain concrete slab and shoulders are kept tight or closed. For heavy truck traffic, dowels may be required to prevent some joint faulting. But if that occurs for very higher volume traffic, because faulting is not a design criteria in short jointed plain concrete pavements at this time, the user or designer should consider using jointed plain concrete pavement overlay of a flexible pavement itself, and not the short jointed plain concrete pavements. So these are some of the design features. These are listed under the SPJP design properties under the design features folder. This is the tab. The joint spacing, again, sealant type, which is the typical entry or input used for other concrete pavements, whether we have tight shoulders and the low transfer efficiency. And then the other difference, or the main difference, besides the short joint spacing, is the transverse joint low transfer efficiency. This can be an annual value, which is the typical one used, or the low transfer efficiency can be a seasonal value. And that low transfer efficiency is entered for each of the seasons, or the overall average annual value is entered on an annual basis. And this is for the short jointed plain concrete pavement overlays of asphalt pavements. The other is the Rehabilitation tab, and this is the fatigue cracking. The user can enter the amount of bottom-up fatigue cracks in the existing asphalt pavement, as well as the amount or length of transverse cracks in the existing asphalt pavement. The program will use bottom-up fatigue cracks to look at the damage in the existing asphalt pavement. However, there will only a specific amount of fatigue percent cracking is used in the design computations, which will be explained and defined on the next slide. So the user can enter total amount of bottom-up fatigue cracks in the existing asphalt, but the program uses a constant value for bottom-up fatigue cracks. And so that is based on the amount of cracking, rehab input level 2, and the percent of 65% cracking was derived from calibration and was the value that best fit the amount of observed fatigue cracks in the short jointed plain concrete overlays of flexible pavements. The reason for that excessive fatigue cracking is really unknown at this point in time. So we just want to note that a value of 65% is used and was defined through global calibration. And maybe this has to do with the bond between the concrete and existing asphalt surface. Maybe it's related to some other mechanism. But the important point is 65% fatigue cracking is used to characterize the existing asphalt pavement when short jointed plain concrete pavement overlays are used above flexible or asphalt pavement. Other factors affecting the concrete bending stress, but not considered by the Pavement ME design software is material disintegration throughout the design life of the existing asphalt and or loss of friction between the concrete and existing asphalt overlay. Those are not considered in the short jointed plain concrete pavement overlay design of asphalt pavement. The Pavement ME procedure covers three types of commonly defined concrete bonded overlay designs based on joint spacing, not thickness. Longitudinal joint spacing is 2 to 4 feet. Corner cracking is the key to stress. That is not included in the Pavement ME design software. Longitudinal cracking greater than 4.5 to 7 feet. This is the longitudinal cracking is the critical performance criteria and is the key to stress that is included in the Pavement ME design software. Longitudinal joint spacing is full lane width. Transverse cracking is the key to stress. However, this is included in the Pavement ME software, but for the traditional jointed plain concrete overlays of flexible pavements, which are generally greater than 6 inches in thickness. So very short longitudinal joint spacing, 2 to 4 feet. They're not considered in Pavement ME. The joint spacing that is about 4.5 feet to 7 feet. And if the longitudinal spacing is at the full lane width, then that should be treated as a traditional jointed plain concrete pavement overlay of an existing flexible pavement and not short jointed concrete pavement overlay of an asphalt pavement. So now let's move to the summary of this section. We're going to go through a couple of topics, items to remember that we mentioned earlier in the module. First, the damage determination of the existing asphalt layer. The software determines the damage in the existing asphalt pavement from bottom-up fatigue cracking values entered and then accumulates that additional damage of the asphalt layer from that starting point. As a reminder also, the rutting damage is determined in the same manner, but from the rutting assigned to individual layers. The strain hardening concept is used to determine the starting point for the rut depth accumulation in the existing pavement layers. That includes both the asphalt as well as the unbound layers. The design criteria for the asphalt overlay is the same as for new flexible pavements, except for that including reflection cracking. The new cracks and the reflection cracking are added together, and that is the amount of cracking for which the reliability is determined or applied. The design criteria for the concrete overlay is the same as for new concrete design, either the JPCP or CRCP. Reflection cracks are not considered in the concrete overlay designs. The unbound layer inputs, the default resilient modulus and volumetric property should represent the condition from at the time of testing. The laboratory measured resilient modulus and volumetric properties are the default values. The back calculated values from deflection data and the in-place volumetric properties measured at the time of FWD testing should be used when those back calculated values are converted to a laboratory equivalent value, and the C factors are values to determine that adjustment are listed in table 10-8 in chapter 10. So the resilient modulus entered into the software for new design as well as rehabilitation design needs to represent the volumetric properties at which the resilient modulus was established. either through laboratory testing or back calculation of elastic layer moduli values. So in summary, in this section, we described the models and transfer functions for asphalt pavement rehabilitation, or those that are specific to asphalt pavement rehabilitation. We described the flexible pavement rehabilitation design strategies. We identified the differences between flexible pavement rehabilitation and new flexible pavement design. We also described the different rehabilitation input levels, both for flexible pavement rehabilitation designs in terms of asphalt overlay versus concrete overlays. We listed the important factors to consider in the design of surface modifications of asphalt pavements using the Pavement ME design software. We listed the important factors for consideration in the design of structural asphalt overlays for existing flexible pavements. And finally, we listed the important factors in the design of concrete overlays of flexible pavements. With that, this concludes the workshop on Pavement ME design. We thank you for attending the entire workshop. And if you have any comments or questions, please direct those to the Pavement ME design website itself. So again, thank you for attending the workshop, and this concludes the workshop on Pavement ME design.